In 1962, a storm parked off the mid-Atlantic and hit the coast with 5 consecutive high tides. 40 people died, 1.8 billion in damage. That coast no longer exists. The sea level at Norfolk has risen nearly 5 millimeters per year since then. New York City paved over 61% of its ground, and the sewer system that's supposed to handle the runoff overflows half the time it rains. Before any storm arrives, I pulled every data set I could find on what happens when a storm that doesn't move lands on a coastline that's been fundamentally redesigned since the last time it happened. 4 historical case studies, 3 compounding mechanisms, and a modeling gap that means nobody, not FEMA, not NOAA, not a single published study, has run the compound scenario for the I-95 corridor. This is what I found. If the idea that every flood map on the East Coast assumes the storm keeps moving got you locked in, take a second and hit subscribe to Orbital View. We're tracking the compound flood risk across the entire I-95 corridor this season and beyond. Drop a comment with your city and whether you've ever seen water that wouldn't drain, standing floodwater that just sat there for hours because the system couldn't push it out. I read everyone. A storm system that detaches from the jet stream, loses its steering current, and parks over the most densely populated corridor in the Western Hemisphere, pumping moisture over the same ground for 96 hours straight. The 1962 storm that hit the mid-Atlantic with 5 consecutive high tides and why the coast it struck no longer exists in the form the planning documents assume. And the hidden math behind 61% impervious cover, a 150-year-old sewer system that overflows half the time it rains, and a sea level baseline that has already climbed a foot since the last time this happened. Let's get into it. Part 1. The pattern nobody's watching. I pulled the Weather Prediction Center's extended forecast discussion on June 4th, 2026 at 3:56 in the afternoon Eastern Time. The WPC, College Park, Maryland, issues national forecast guidance for precipitation and severe weather. Their discussions are the documents that tell you what the professional forecast community is actually looking at, in their own operational language, without the television graphics and the simplified maps. And on June 4th, the headline feature wasn't a flood threat. It was heat. An amplifying upper ridge was settling over the eastern United States. Warm southerly flow was pouring into the mid-Atlantic. Overnight, low temperatures stuck in the 70s. The WPC flagged moderate to major heat risk, levels 2 through 3 out of 4, across portions of the mid-Atlantic coast for that coming Friday and Saturday night. You can pull this discussion up yourself on the WPC website. It's public. It's archived. And what it describes is not the storm scenario this episode explores. So right now, the pattern over the East Coast is a ridge, a dome of heat, not a flood, not a stall. But I kept reading, because there's a second feature in that same discussion, buried deeper in the medium range section, that is doing very quiet analytical work. On the backside of that ridge, the WPC describes a Western Atlantic amplified upper trough. Deep energy rotating on the ocean side of the high pressure, linking with southern stream shortwave energy, pushing toward the southeast. The CPC's probabilistic hazards and outlook for week 2 picks up the same signal from a different angle. Slow-moving, low-pressure development in the eastern Gulf of Mexico. The European model painting 4 to 6 inches of rain across South Florida, a stalled frontal boundary centering across the Miami metro. That trough is aimed at Florida right now, not the I-95 mid-Atlantic corridor. And the models. This next part is genuinely important to how you hold the rest of this investigation. The models are fighting each other about what happens next. The WPC says it directly. After midweek, models significantly diverge from each other on the timing, placement, and intensity of the heaviest rainfall. That's not my editorializing. That's the operational guidance verbatim from the people who write the national forecast. Hold that divergence, because it is the seed of everything this episode explores. I've been reading WPC discussions for years, and that specific phrase, models significantly diverge, appears more often than you might expect, but it almost always appears in the context of the same family of weather patterns, slow-moving lows interacting with blocking ridges. These are the setups where the atmosphere sits at a fork in the road and the models can't agree which branch it takes. One solution moves the low out to sea in 48 hours. Another solution parks it for 5 days. Both solutions are physically plausible. Both fit the initial data, and the distance between them, measured in human consequences, is enormous. When forecast models diverge at medium range, it means the atmosphere is sitting near a decision point. Small changes in the initial conditions, a jet stream wobble of a few degrees latitude, a ridge that amplifies a bit more than expected, send the solution scattering. And the specific kind of divergence the WPC is flagging here, a slow-moving low interacting with a ridge, is the exact setup that produces the most dangerous weather pattern the East Coast faces, one that most people outside the operational forecast community have never heard of. NOAA's May 21st seasonal outlook calls for below normal Atlantic hurricane season, 55% probability, 8 to 14 named storms, citing developing El Nino and increased vertical wind shear. The Atlantic basin in early June is quiet. The tropics are dormant. But here's what I need you to understand. The atmosphere doesn't need a hurricane to build the scenario I'm about to walk you through. It needs a trough that cuts off, a block that holds, and a coastline shaped like a catcher's mitt. All three ingredients exist in the current medium-range guidance. They're just aimed at the wrong target. Shift that western Atlantic upper trough several hundred miles north. Let it deepen over the mid-Atlantic bight, the concave stretch of coastline between Cape Hatteras and Cape Cod. Let a blocking ridge lock into place upstream. And instead of a Florida rain event, you have a storm system parked directly over the corridor where 53 million people live, where the KDIX NEXRAD radar at Fort Dix tracks precipitation for Philadelphia and the NWS Mount Holly forecast area, where KOKX at Upton covers New York City and Long Island, where KLWX at Sterling handles Washington and Baltimore, where KAKQ at Wakefield watches Hampton Roads and Norfolk, the fastest sinking stretch of the eastern seaboard. I am not telling you this is happening. The operational data does not support that claim today. What I'm telling you is that the distance between the pattern that exists in the medium-range guidance right now and the worst flooding scenario this coast has seen since 1962 is not a different atmosphere. It's the same atmosphere with a few hundred miles of lateral displacement in the upper level flow. And that question, what happens when a storm system loses its steering current and parks over this coastline, has answers. Specific, devastating, well-documented answers written in tide gauge data and damage reports and body counts. Every one of those answers gets worse when you update the baseline to 2026. The sea level is higher. The ground absorbs less water. The drainage systems are older and closer to failure. And the reason this combination is so dangerous is not the one most people expect. It isn't about the storm getting stronger. It's about the storm sitting still. Part 2, what it means to cut off picture a river. Fast-moving current, steady flow. Now, picture an eddy, a pocket of water that spins off the main Amo channel and just sits there, rotating in place while the river rushes past it. The main current doesn't grab it back. The eddy doesn't rejoin. It just parks in the shallows, spinning on its own energy until friction slowly kills it, or something upstream shifts and recaptures it. That is a cut-off low. That's what the entire investigation is built on. The jet stream is the river. Normally, weather systems ride it, west to east across the continent, steered by the upper-level flow the way a log rides a current. They move through. That's the key assumption built into every flood model, every drainage design, every coastal planning document on the East Coast. The storm moves through, but sometimes a deep trough in the jet dives so far south that the flow narrows and pinches off behind it. The trough detaches. The system drops out of the current. The National Weather Service defines it as a closed upper-level low, which has become completely displaced from basic westerly current and moves independently of that current. Independently. That word is doing all the work. It means there is no steering mechanism. The storm goes wherever its own internal dynamics take it, which is frequently nowhere at all. The typical life cycle of a cutoff low runs 2 to 4 days before friction or a pattern change kills it or reabsorbs it into the jet. But when a strong blocking pattern holds upstream, that life cycle stretches. 5 days, 7 days, in rare cases more than a week. And every additional day the system sits in place, it cycles more moisture through its circulation, delivering another round of rain over the exact same ground. The cumulative totals aren't additive. They're compounding because the ground saturates, the drains fill, the rivers crest, and each new inch of rain lands on a surface that has less and less capacity to absorb or move it. And here's the piece that should concern anyone who depends on weather forecasts to make decisions. The models handle this badly. It's not a secret in the operational community. Published analysis from forecasters who work with these systems daily confirms what the NWS has known for decades. Numerical weather models tend to forecast the closed low pressure to rejoin the jet stream too quickly. The models want to push the eddy back into the river. They're biased toward restoring the normal flow, but the eddy doesn't care what the GFS or the European model wants. It sits there, drawing moisture from the ocean, cycling it through its circulation, and dumping it on the same ground, hour after hour, tide cycle after tide cycle, for as long as the block upstream holds. So what holds the block? Think of a semi-truck double parked on a 3-lane highway. Brad Panovich at WCNC in Charlotte uses that metaphor, and it's the right one. Because a blocking ridge doesn't just slow the jet stream, it forces everything behind it to stop or reroute. Meteorologists have specific names for the patterns that form. An omega block looks like the capital Greek letter omega drawn across the jet stream, a big fat ridge in the middle flanked by 2 troughs, the whole arrangement locked in place like 3 gears meshing. A Rex block, named for the meteorologist Daniel Rex, who first described it in 1950, stacks a high-pressure system directly poleward of a low east, a configuration. The Weather Network has compared to a kink in a garden hose. The flow backs up, nothing moves. NOAA's jet stream training material, the same material used to educate operational forecasters, states it plainly. Strong, particularly persistent Rex blocks can cause flooding near the low-pressure part of the block. That's not a hypothetical. That is institutional guidance from the agency responsible for the forecast. A 2024 study by Pinheiro, Hodges, and Gahn, published in Weather and Climate Dynamics, tracked how cutoff lows deepen once they've detached. Their key finding: the presence of a nearby jet is crucial for providing the energy necessary for the intensification and deepening of the system. Read that again, carefully. The jet stream creates the cutoff, feeds it energy from nearby, and the block prevents the jet from recapturing it. The system sits in place, powered by the very current that abandoned it, and the models, which were already biased toward moving it along, keep underestimating how long it stays. This is not a theoretical failure mode. In September 2023, an omega block parked over Central Europe. A cutoff low trapped beneath it sat over the eastern Mediterranean for days. The result was Storm Daniel. Catastrophic flooding across Greece, Libya, Turkey. Thousands dead. Same mechanism. Same model verification gap between what was forecast and what was delivered. And every one of these events shares the same structural problem. The difference between a storm that runs through your yard with a hose and a storm that stands still and points the hose at your basement for 3 straight days is not a difference of degree. It is a difference of kind. Every defense the coast has was built for the first version. The last time this exact configuration assembled over the mid-Atlantic bight, it was March of 1962, and the coast has never been the same since. Part 3, the 5-high storm, March 6, 1962. Ash Wednesday. A nor'easter develops off the Carolina coast, nothing unusual for early March along the seaboard. These systems form, track northeast, move offshore, and dissolve. The textbook says so, the pattern says so, but this one doesn't follow the textbook. The upper-level pattern locks it in place roughly 100 miles east of the Delmarva Peninsula, and for the next 36 hours, its circulation grinds against 600 miles of coastline like a blade that won't lift off the wood. And the timing? I need to walk you through the timing, because it is what separates a bad nor'easter from a coastline-altering catastrophe. The moon was at perigee, its closest orbital approach to Earth that month. and it was aligned with the sun, a spring tide configuration. So before the storm even arrived, the ocean was already running high. The baseline was elevated. That matters because what happened next wasn't one big hit. It was five consecutive high tide cycles. Roughly 36 to 40 hours of storm duration meant the coast took tides on the 6th, the 7th, and into the 8th of March. Each high tide pushed water onshore under sustained onshore winds. Each low tide should have let the water drain back. But the winds never stopped, and the next tide arrived before the previous one had fully receded, water stacked on water. The second cycle was worse than the first. The third was worse than the second. By the morning of the 7th, communities that had survived the initial hit were watching the ocean come back, higher than before, into streets that hadn't drained from the night. By the 4th and 5th tidal cycles, entire sections of Barrier Island were being physically rearranged, not just flooded, reshaped. The beach at Rehoboth, Delaware, disappeared under the boardwalk. The dunes at Assateague were cut through. In Long Beach Island, New Jersey, the ocean met the bay. The island breached. Entire blocks of homes sat in open water where there had been dry land 36 hours before. Ocean City, Maryland, recorded tides 9.5 feet above average low water at peak. Gusts hit 64 miles per hour. At the Delaware Breakwater Station, sustained winds reached 72 miles per hour, and the tide gauge measured 9.3 feet above normal before the instrument failed. The estimated true peak, after the gauge died, was 11 feet. A 600-mile fetch built open ocean waves up to 30 feet. Inland, where the storm wrapped moisture around its backside, 42 inches of snow buried Virginia's Blue Ridge. This system was doing everything simultaneously. 40 people died. More than 1,000 were injured. Across the affected states, 1,793 homes were destroyed outright. Not damaged, destroyed. 16,782 more were damaged. New Jersey alone reported $130 million in property losses in 1962 dollars. The total inflation-adjusted cost across the mid-Atlantic comes to roughly $1.8 billion. Maryland Governor Millard Tawes called it the worst disaster in the history of Maryland in his time. The USGS ranked it among the most destructive 20th century storms to strike the mid-Atlantic coast. And the National Park Service notes that the U.S. Weather Bureau took the extraordinary step of formally naming an extratropical cyclone, a move with no precedent in Weather Bureau history. I keep coming back to what this storm was not. It was not a hurricane. Sustained winds stayed below hurricane force at every reporting station. The single-period rainfall totals, while significant, didn't break records for their measurement intervals. If this nor'easter had moved through at normal translational speed, passed in 24 hours and gone, it would have been a rough March storm. Damaging in spots, forgettable by May, maybe not even the worst storm of that season. Stationarity is what turned it into something else entirely. 5 waves of the same punch, delivered over 3 days, and the coast never got a standing 8 count between rounds. The water never went home. The sand never resettled. The next hit arrived while the previous one was still being absorbed. That is the thesis. That is what the rest of this investigation is going to prove from 6 different angles. But there's something that sits with me even more than the damage numbers. 40 people died in 1962. The Ash Wednesday storm hit a coast that no longer exists in the form it existed that March. The sea level at the Battery has climbed nearly 3 millimeters per year, every year, since then. At Norfolk, the rate is nearly 5, and the surface those tides washed across, the sand and the marsh grass, and the Barrier Island soil, is no longer sand and marsh grass and soil. In New York City, 61% of the land surface is now impervious. Concrete, asphalt, rooftops, material that sheds water instead of absorbing it. The coast the 5-high storm struck is gone, and what replaced it is harder, higher, more populated, and fundamentally less capable of absorbing what a parked storm delivers. Part 4. The coast that no longer exists. NOAA operates a network of tide gauges along the eastern seaboard, and you can pull this data yourself, station by station, on the KEO Ops website. The records are public. They update continuously. I spent 2 full days going through them station by station for this investigation, and the picture they paint is not ambiguous. It is not a matter of interpretation. The water is measurably, documentably, steadily higher than it was when the Ash Wednesday storm hit. The Battery, New York, station 8518750, records through 2025, relative sea level rise 2.95 millimeters per year, plus or minus 0.09. That translates to just under a foot per century. That sounds slow until you realize it never stops and it never reverses. Sandy Hook, New Jersey, station 8531680E, runs faster, 4.28 millimeters per year. Atlantic City, just down the shore, 4.25. Baltimore, tucked inside the Chesapeake, 3.31. And then there's Norfolk, Sewell's Point, station 8638610, 4.84 millimeters per year, plus or minus 0.20. That is 1.59 feet per century gust, among the fastest sustained rates of relative sea level rise on the entire eastern seaboard. And the reason Norfolk runs so high tells you something important about how this threat compounds. Part of what the gauge measures is the ocean rising, but part of it is the land dropping. Norfolk sits on ground that is still rebounding, or more accurately, still sinking, from the weight of glacial ice sheets that melted roughly 12,000 years ago. Add in decades of municipal and industrial groundwater withdrawal that compress the underlying aquifer, and the result is a gauge that's catching movement from both directions. The ocean comes up. The ground goes down. The instrument doesn't care which one is doing the moving. It just records the gap. In 2012, Asbury Salinger at the U.S. Geological Survey published a paper in Nature Climate Change that changed the conversation about East Coast sea level. He identified what he called a hotspot of accelerated sea level rise on the Atlantic coast of North America, a stretch roughly from Cape Hatteras to Boston, where the water isn't just rising. It's rising faster than it was before. The rate of rise is itself increasing. John Boone, an emeritus researcher at the Virginia Institute of Marine Science, pinpointed the inflection in the tide gauge data around 1987. Before that year, the trend was steady. After it, the curve bends upward. Something shifted in the system, and the leading hypothesis in the literature points to changes in the large-scale ocean circulation. A weakening Gulf Stream that's piling water against the East Coast instead of carrying it northward and away. Now, I want to be careful here because there is a dissenting view and it deserves honest treatment. Albert Parker published a paper in 2012 arguing that a roughly 60-year oscillation visible in the tide gauge records could account for the apparent acceleration, that what appears to be a long-term trend might instead be the rising limb of a natural cycle. The mainstream consensus does not favor Parker's interpretation, but his paper is peer-reviewed, and a careful viewer holds it in the other hand while evaluating the weight of the evidence. Both things can be true. The acceleration is real in the data, and longer period oscillations exist, and the two are hard to cleanly separate with the record lengths we have. That kind of honest ambiguity is exactly what the science shows, and I'm not going to flatten it. What the consensus does very clearly support is the NOAA 2022 Sea Level Rise Technical Report. William Sweet was the lead author. The projection for the East Coast, 10 to 14 inches of additional rise by 2050, as much rise in the next 24 years as the entire previous century delivered. Nicole LaBouffe, the director of NOAA's National Ocean Service, put the implication this way: moderate flooding, which is typically disruptive and damaging by today's weather, sea level, and infrastructure standards is expected to occur more than 10 times as often as it does today. Think about what that means for a 5-high scenario. Every inch of sea level rise raises the starting line. A tide that crested at 9.3 feet above normal in 1962 crests higher now, not because the storm is any stronger, but because the ocean underneath it is taller. Norfolk already floods on sunny days. Clear skies, no rain, no storm, just the king tide creeping into the streets because the margin between normal high water and infrastructure elevation has been eaten by 6 decades of compounding rise. Roads that were dry 20 years ago spend hours underwater now on a regular basis without a single drop of rain. That's what an extra few inches does when the margin was already thin. The tide gauges are the thermometers nobody checks until the fever breaks. And the fever has been building for 60 years without interruption. But the rising ocean is only half the equation, because the water that climbs from the coast eventually meets the water that falls from the sky, and sitting between the two, asked to manage both, is the oldest, most overtaxed drainage infrastructure in America. It was designed for a world that no longer exists, a world where the rain soaked into the ground, the storms moved through in a day, and the ocean stayed where it was. Part 5. The system that overflows. Half the time it rains, New York City's combined sewer system is roughly 150 years old. Some sections predate electric street lighting, and the word combined is the problem. It means the same network of pipes carries both rainwater runoff and raw sewage, domestic waste, industrial discharge, everything, through a single set of conduits to the treatment plants. When it rains hard, and sometimes when it barely rains at all, the volume of stormwater entering the system exceeds what the treatment plants can process. The excess, a slurry of rainwater and untreated sewage, goes directly into the waterways. The East River, the Hudson, the Bronx River, the Gowanus Canal, Newtown Creek, 398 outfall pipes ring the city's shoreline, according to the New York State Department of Environmental Conservation. And the volume those pipes discharge in a typical year averages approximately 18 billion gallons of combined sewage overflow. That number, $18 billion, is from the DEC. The Natural Resources Defense Council puts the annual volume of sewage and stormwater reaching NYC waterways even higher, at roughly 27 billion gallons. The discrepancy reflects different accounting methods, but the order of magnitude is consistent and staggering either way. And here's the thing about that number that nobody on television ever contextualizes. The system doesn't need a disaster to overflow. It overflows about half the time it rains, not during once-a-century storms, not during hurricanes. Routine rain, the margin between function and failure, is that thin under normal conditions, before any extreme event arrives. Philadelphia runs a parallel crisis. 13 to 14 billion gallons of combined sewer overflow annually, despite the city's landmark $2.4 billion Green City Clean Waters program, the most ambitious green infrastructure investment of its kind when Howard Newkrug, then the water commissioner, designed and launched it. Green roofs, rain gardens, permeable pavement, tree trenches, the program is real, the investment is massive, and it still can't keep pace. The Philadelphia Water Department's own climate modeling projects a 9.5% increase in average annual rainfall by 2050. The rain gets heavier, the pipes stay the same diameter. In Washington, progress is more visible. DC Water's Clean Rivers project is constructing an 18-mile tunnel network beneath the city, 249 million gallons of underground storage capacity, designed to capture overflow during storms and feed it back to the treatment plant when the rain stops. The target is a 96% reduction in combined sewer overflow events. That's real progress, genuinely impressive engineering. But the tunnels are not complete, and the storms are not waiting for a ribbon cutting. Scale this nationally, and the picture doesn't improve. The EPA estimated in 2004 that roughly 850 billion gallons of combined sewage and stormwater discharge into American waterways every year, from approximately 700 combined sewer communities spread across the Northeast, the Great Lakes region, and the Pacific Northwest. The average age of the water and sewer pipe buried under American cities is about 50 years. Some of what runs beneath the I-95 corridor was laid before the automobile existed. And then there's the surface itself. Rain, in its natural cycle, is supposed to soak into the ground. Soil absorbs it, root systems channel it, groundwater recharges. But when you pave over the ground, the rain hits an impervious surface and runs. Instantly, 100% of it becomes runoff. New York City's impervious surface coverage, asphalt, concrete, rooftops, every surface rain cannot penetrate, stands at 61.1%. the highest of 20 major American metropolitan areas, studied in a 2012 analysis published in Urban Forestry and Urban Greening. The Center for Watershed Protection calculated that 65% of all impervious cover in the United States is what they call habitat for cars. Streets, parking lots, driveways. We paved the ground so cars could sit on it, and now the rain has nowhere to go. NASA and EPA researchers working on the Chesapeake Bay watershed established the thresholds: measurable stream degradation, fish kills, erosion, loss of aquatic habitat begins at 10 to 15% impervious cover. Severe impairment sets in above 25%. New York City is at 61, so the ground isn't a sponge anymore. It's a parking lot, literally, and the drain it feeds into is a 150-year-old pipe that's already being asked to swallow a modern city's rain and sewage through the same hole, and it fails at that job half the time it rains under normal conditions. Now build the cutoff low scenario on top of this. Not hours of rain, days, not a storm that passes through, because the drainage was designed a century and a half ago for storms that pass through. A storm that parks. The rain falls on 61% impervious cover and sheets into combined sewers already operating at capacity. The coastal water level, meanwhile, is elevated by persistent onshore winds, the same mechanism that stacked 5 tidal cycles in 1962, which means the outfall pipes that are supposed to drain into the harbor cannot drain. The harbor water level is higher than the pipe openings. The bathtub can't empty because the drain itself is underwater, and the faucet never turns off. Picture it from street level. Day 1, the rain starts. The sewers take it for the first hour, maybe 2. Then the manholes begin to bubble. Water backs up through the grates, pooling in the low spots, the underpasses, the below-grade entrances. The combined system is now at capacity, and every additional gallon of rain that hits an impervious surface goes directly to the street because there's nowhere else for it to go. Day 2, the storm hasn't moved. The rain hasn't stopped. The streets are flooded, but the tide is also elevated, which means the water sitting in the streets cannot flow downhill to the harbor. The gradient is gone. The harbor is as high as the streets. Day 3, the rain continues. High tide returns. The harbor rises again. The streets that never drained from day 2 take a fresh layer. Subway entrances become intake points. Basement apartments, the ones below the sewer line, the ones that were never designed to be residences, but that house hundreds of thousands of people across the I-95 corridor, many of them immigrants, many of them low income, many of them invisible to the emergency alert systems, fill from the bottom up. There is an answer to what the early stages of that scenario look like, just the first few hours of it. It came on September 1st, 2021. The remnants of Hurricane Ida dropped more than 7 inches on Central Park in a few hours, and 13 people drowned in basement apartments, most of them in units that were never legally designated as residences, most of them foreign-born. The infrastructure didn't just fail, it failed along the lines of who had the least protection and the fewest options. And who it failed is as important to this investigation as how. Part 6, 7 inches and 13 lives. September 1st, 2021. A Tuesday night, the remnants of Hurricane Ida, a storm that made landfall in Louisiana 48 hours earlier as a Category 4 with 150 mile per hour sustained winds, are racing northeast across the Appalachians. Ida is no longer a hurricane by any technical definition. The closed surface circulation is gone. The eye wall structure is gone. What remains is a massive, disorganized mass of deep tropical moisture riding a frontal boundary draped across the mid-Atlantic and northeast. The NWS offices along the I-95 corridor, Mount Holly in New Jersey, Upton on Long Island, Sterling in Virginia, are issuing watches. Flash flood watches. The language in the forecast discussions is cautious but alarmed. Training thunderstorms are expected. Rainfall rates could reach 2 to 3 inches per hour in localized bands. But nobody is prepared for what happens between approximately 8 and 11 p.m. that night across the New York City metropolitan area. Not the models, not the public messaging, not the emergency management structure that's supposed to translate forecast language into human action. Central Park's weather station has operated continuously since 1869, more than 150 years of rainfall data without a gap. On the night of September 1st, 2021, that station recorded 3.15 inches in a single hour. That broke every hourly rainfall record in the station's entire history, not by a margin that invites debate, by a margin that rewrites the statistical context of what the city's infrastructure was designed to handle. Then the daily total came in, 7.13 inches for the calendar day. The prior all-time daily record for Central Park was 3.84 inches, set in 1927. Ida didn't edge past it. Ida nearly doubled it, and Central Park wasn't even the worst hit station in the metro area. Newark, New Jersey, the major reporting station for northern Jersey, logged 8.41 inches for the day, obliterating a record of 2.22 inches that had stood since 1959. The old record wasn't even close. The National Weather Service issued New York City's first ever flash flood emergency. In the hierarchy of NWS flood alerts, a flash flood emergency sits at the very top, above flash flood warnings, above flood advisories, reserved for situations of imminent and severe threat to human life. That product had never been activated for the 5 boroughs before that night. Think about that for a moment. A century and a half of continuous weather observation in New York City, thousands of rainstorms, dozens of tropical systems, and not once until September 1st, 2021, had the NWS determined that conditions warranted the highest tier flash flood alert in the warning portfolio. The forecasters at NWS Upton, working with radar returns from the KOKX NexRad site, were watching cells train over the same neighborhoods in succession, thunderstorm after thunderstorm, moving over identical ground like boxcars on a rail, stacking rainfall totals that exceeded anything the drainage infrastructure was rated for. The operational forecasters could see it happening in real time on the radar, but the rain was falling faster than the warning system could translate it into evacuations. The gap between issuing the alert and the water reaching lethal depth was measured in minutes, not hours. And the issue wasn't just total volume, it was rate. 3 inches per hour on a surface that is 61% impervious means the water has nowhere to infiltrate. Every drop becomes runoff. Every runoff stream flows downhill, through every opening, into every low point, into every gap in the pavement, and the lowest points in New York City are the places where people live who cannot afford to live anywhere else. 40 people died across the Northeast that night and the following morning. 23 in New Jersey, many in vehicles caught in flooded roadways where underpasses had filled in minutes. At least 13 in New York City, including a 2-year-old child in a basement apartment in Queens. A 2-year-old. Deaths were also reported in Pennsylvania, Maryland, and Connecticut. The geographic spread tells you something about the scale of the rain footprint. Ida's remnants were dropping record or near record rainfall across a 300-mile corridor simultaneously. And the details of how people died, the specific mechanism of their deaths, reveal something about the infrastructure that aggregate numbers don't. This is the part of the investigation that is hardest to sit with, and I'm going to walk through it carefully because the pattern is precise and it has direct implications for the cutoff low scenario. A peer-reviewed analysis published through PubMed examined the 14 Ida-related injury deaths documented in New York City. 13 of the 14 were directly caused by flooding. Of those who died, 71%, nearly 3 out of every 4, drowned in basement-level apartments. Units that were, in many cases, never legally approved as residences. Converted spaces below the sewer line, below grade, below the level where water accumulates first when the system above them fails. The same review found that 71% of the deceased were foreign-born. These weren't tourists. These weren't commuters caught in the wrong place. These were New Yorkers, immigrants, workers, families, living in the most vulnerable housing stock in the city because it was what their income could access. The water went where gravity took it, and gravity took it to the people with the fewest exits and the least visibility in the emergency alert system. New Jersey Governor Phil Murphy called it an extraordinary, sadly tragic, historic 24 hours. The word I keep returning to is not extraordinary. It's selective. The system failed selectively. The infrastructure protected the people who lived above grade, in newer buildings, in neighborhoods with better drainage. It failed the people who lived below. And below meant several things that night. Below grade in basement apartments. Below the sewer line in units that were never designed for habitation. And below the street in the subway system. Water cascaded down stairwells into stations across Manhattan, Brooklyn, and Queens. The MTA shut down service. Riders were stranded in trains, sitting in flooded tunnels. Water rising to the platform edges, pouring through ventilation grates, turning stations into underground pools. The subway system, which moves roughly 3.5 million riders on a typical weekday, was designed to handle rainwater intrusion at rates consistent with storms that move through. Ida sat on top of it and poured in water at rates the system had literally never experienced. The drainage pumps couldn't keep up. The system filled from the bottom. But the connection you need to carry forward from this section is about duration. Ida's remnants moved through relatively quickly. A few hours of extreme rainfall, and the sewer system was overwhelmed. The subways flooded. The basement apartments filled. The roads became rivers. People died. And then it was over. The rain stopped. The skies cleared by morning. The water began to drain, slowly, unevenly, but the system recovered because the input stopped. A cutoff low doesn't stop. It doesn't clear by morning. It parks. Everything Ida delivered in 6 hours, the scenario I'm building delivers for days. Ida was a glimpse of the failure mode, like watching a levee overtop for 10 minutes and then trying to imagine the consequences when it overtops for 72 hours straight. The same infrastructure. The same impervious cover, the same basement apartments, the same combined sewer outfalls already at capacity, but sustained, unrelenting, multi-day rainfall with no break between rounds and no morning clearing to let the system catch its breath. The clearest proof of what the multi-day version of that failure looks like didn't happen on the I-95 corridor. It happened 600 miles south, in South Carolina, in October of 2015. The mechanism was identical to the scenario. This entire episode is built around a cutoff low acting as a moisture pump. And the damage was staggering. Part 7. Baking cookies on an assembly line that never stops. I want to be precise about what happened in South Carolina in early October of 2015 because this event is the mechanistic twin of the cutoff low scenario I've been constructing for you. The physics are the same. The atmospheric pattern is the same. The only meaningful difference is geography. South Carolina sits further south, on sandier soil, with lower impervious cover, and a different coastal geometry than the mid-Atlantic bight. Those differences mattered. They're the reason the death toll was 19 and not 10 times that. And they are the differences that would not apply if the same mechanism parked over the I-95 corridor. Here's the setup. A cold front had pushed offshore and stalled along the southeast coast. Behind it, a cutoff upper-level low settled over Georgia and the western Carolinas, the exact type of system Part 2 of this investigation explained. That low, spinning in place, with no jet stream steering current to push it along, set up a persistent atmospheric circulation that reached out over the warm Atlantic and funneled tropical moisture westward into the Carolinas like a conveyor belt. A fire hose of warm, saturated air aimed at the same target, hour after hour, day after day, and feeding that conveyor belt from the east, pumping moisture into the system, was Hurricane Joaquin. Joaquin was a powerful storm churning through the Bahamas with sustained winds near 130 miles per hour at its peak. It never made United States landfall, not even close, but it didn't need to make landfall to matter. Its moisture, the vast reservoir of tropical water vapor in its outer circulation, streamed northwest, got captured by the cutoff low's rotation, and poured into the Carolinas. Two systems, hundreds of miles apart, working in concert through a shared atmospheric mechanism. NOAA's climate.gov team later described this setup with what I think is one of the best plain language explanations of cutoff low flooding any government agency has ever published. They compared it to baking cookies on an assembly line that never runs out of ingredients. The moisture supply was limitless. The low kept spinning. The assembly line kept running. And the rain kept falling on the same ground for 4 straight days. Day 1, Thursday, October 1st, was heavy rain. Unusual, persistent, but not yet catastrophic. Day 2 brought intensification as the tropical moisture feed from Joaquin strengthened. By Saturday, October 3rd, the rivers were in flood stage across multiple basins. The ground was fully saturated, and every additional inch of rain became runoff because the soil simply couldn't hold any more. And still the low sat there. Still the moisture arrived. The NWS office in Colombia was issuing products at a pace and severity they'd never matched. Record event language, life-threatening language, language that strained the warning system's vocabulary because the system wasn't built to describe an event that lasts this long at this intensity. The numbers from those 4 days are hard to process because they exist outside the range of normal meteorological experience. Widespread rainfall totals across the South Carolina Lowcountry range from 15 to 20 inches. Localized pockets exceeded 24. The rain gauge at Boone Hall recorded 24.23 inches for the event. More than 2 feet of water falling from the sky in 4 days. Charleston Airport, one of the region's primary reporting stations, set a new 24-hour rainfall record at 11.5 inches. Columbia, the state capital, broke its all-time records for 1-day, 2-day, and 3-day rainfall accumulation. Records that had stood for decades shattered in a single event at every measurement interval. Some locations reached a statistical recurrence interval of 1 in 1,000 years, meaning the probability of that amount of rain falling in that window at that location in any given year is less than 1/10 of 1%. Governor Nikki Haley addressed the state with a line that cut through the statistical language and landed, "We are at a 1,000-year level of rain." That's how big this is. The human and infrastructure toll was immense. 19 people died in South Carolina, 25 across the broader event complex. Nearly 50 dams breached or failed. Earthen impoundments built for routine storms, overwhelmed by volumes that arrived faster and lasted longer than any design specification anticipated. These weren't major federal dams. They were small, often privately owned, earthen structures, impounding farm ponds and recreational lakes across the Midlands and Lowcountry. When they failed, the impounded water added to the already catastrophic river flows downstream. Each breach cascaded, one dam's failure increasing the load on the next structure downstream. By the time emergency managers had a count, dozens of failures had occurred across multiple watersheds simultaneously. More than 1,500 people required water rescue, plucked from rooftops, from cars stuck in rising water, from homes where the first floor had filled while residents retreated upstairs. Over 500 roads and bridges were closed. The closure that reverberated furthest was a 70-mile stretch of I-95 Saster, the main north-south artery of the eastern seaboard, the backbone of freight logistics from Florida to Maine, shut down between I-20 and I-26. That closure didn't just affect South Carolina. It rippled up and down the entire coastal supply chain. More than 20,000 people were displaced from their homes. Total damage was estimated at approximately $2 billion. And this is where the compound element enters the picture with particular force. The 2015 event was not just a rain event, it was a coastal event happening at the same time. The Charleston Harbor tide gauge, the same NOAA co-ops network I walked you through in Part 4, peaked at 8.29 feet above mean lower low water on October 3rd. That peak coincided with a perigean spring tide, the same lunar geometry, the same moon at perigee, sun-aligned configuration that amplified the 1962 Ash Wednesday storm. Persistent onshore winds from the stalled system kept ocean water piled against the coast. The tides didn't fully recede between cycles. The drainage systems that were supposed to push runoff and river discharge out to sea couldn't, because the sea itself was elevated, rain from above, surge from the coast, saturated ground everywhere in between, all three drivers interacting simultaneously. And the conclusion Noah drew from the event is, to my mind, the most important sentence in the entire 2015 post-storm assessment. You do not need a landfalling hurricane for tremendous flooding damage to occur. That is not my editorial framing. That is the institutional conclusion of the federal agency responsible for the forecast. The engine of the 2015 South Carolina flood was not Hurricane Joaquin. It was the cutoff low, the system nobody names, the system that just sat there spinning for 4 days while the moisture kept arriving and the rain kept falling on the same saturated ground. South Carolina had one advantage. The I-95 Mid-Atlantic corridor does not. Soil that could initially absorb rainfall before saturating. The sandy low-country soils acted as a temporary sponge for the first day or so. But Ellicott City, Maryland, a small historic town in the hills west of Baltimore, had no such advantage. And what happened there in 2016, and then again in the exact same location in 2018, reveals the terrain and imperviousness multiplier that completes the compound picture. Part 8, 13 feet in 100 minutes. July 30th, 2016. A Saturday evening in Ellicott City, Maryland. Main Street runs along the narrow valley floor of the Patapsco River, hemmed in by steep hillsides on both sides. The buildings are stone and brick, some dating to the 1800s, pressed tight against the slopes and each other. Restaurants, shops, antique stores, small businesses that had operated there for decades. The town has a documented flood history. The valley has always channeled water when it rains hard. But nobody alive in Ellicott City on July 30th had ever seen what was coming. Between approximately 7:30 and 10 that evening, roughly 6.6 inches of rain fell over the Ellicott City watershed. 5.48 of those inches fell in the first 90 minutes. The NWS Baltimore-Washington Forecast Office, operating out of the KLWX NexRad facility at Sterling, Virginia, classified the event as a less than 0.1% annual exceedance probability. Translating that out of the statistical jargon, this rainfall intensity at this location has less than a 1 in 1,000 chance of occurring in any given year. It's the kind of number that makes hydrologists pause because it pushes against the edge of what the observational record can confidently anchor. The rain hit steeply graded terrain covered by decades of development, roads, parking lots, commercial rooftops, residential surfaces that shed water like glass. And 3 tributaries, Hudson Branch, Tiber Branch, and New Cut Branch, drain the surrounding hills and converge in Ellicott City's downtown before feeding into the Patapsco. Picture 3 fire hoses, each pointed at the same drain from a different direction. Every drop of rain that hits the impervious hillsides feeds one of those 3 channels, and every channel empties into the valley where Main Street sits. The USGS maintains stream gauges on those tributaries. Station 015-89017 on Hudson Branch. Station 015-890109 on Tiber. Station 015-89021 on New Cut. Those gauges record stage height in 5-minute increments, and the data they captured on the evening of July 30th tells the story in numbers that no narrative could improve. The Patapsco River at the Ellicott City gauge rose just over 13 feet in 100 minutes. 13 feet. That's a rate of rise that turns a shallow stream into a wall of water taller than a 1-story building before most people have time to process what is happening, let alone evacuate. But the single data point that stops me, the one I go back to every time I revisit this case, is the 5-minute interval between 8:40 and 8:45 p.m. In those 300 seconds, the river rose more than 2 feet. If you were standing on Main Street at 8:40, maybe ankle deep, water lapping at the curb, by 8:45 you were waist deep, and the current was strong enough to roll vehicles down the street and smash them into storefronts. 2 people died. Jessica Watsula, 35 years old. Joseph Blevins, 38, both swept away by floodwaters on Main Street. Cell phone video from that night, footage captured by people trapped on upper floors of Main Street buildings, shows a river of brown water moving at terrifying speed down the street, carrying cars like toys, smashing them into storefronts and stacking them against bridge abutments. The water isn't pooling. It's flowing, fast, channeled by the valley walls, 8 and 10 feet deep in the lowest sections of Main Street. Buildings that had served as restaurants at dinner time were underwater within minutes. People who had been sitting at outdoor tables an hour earlier were watching the same tables disappear beneath a current strong enough to rip pavement. Their names matter because they represent what happens when infrastructure that was never designed for this intensity of rainfall meets terrain that concentrates every drop. And this case study connects to the thesis with particular force precisely because it is not a coastal event. There was no storm surge in Ellicott City, no tidal stacking, no oceanic component at all. This was pure rainfall-driven flooding, water hitting impervious and semi-impervious surfaces on steep slopes, concentrating through converging valleys and arriving in the floodplain faster than any structure or human could respond. The terrain and the land cover acted as a force multiplier. Rain that might have produced moderate, manageable stream rises in a forested watershed instead became a flash flood of historic magnitude because the surfaces it landed on offered essentially zero absorption and the topography funneled everything to a single point. And then it happened again, May 27, 2018. Same location, same mechanism, 6.56 inches in approximately 3 hours. Same catastrophic flooding on Main Street. Some of the same businesses, barely recovered from 2016, destroyed again. The repetition confirmed what hydrology already predicted. This was not a freak event. This was the landscape expressing its fundamental physics under sufficient rainfall intensity. The geometry of the terrain, the imperviousness of the surfaces, and the convergence of the 3 tributaries, or so, given enough rain, falling fast enough, the outcome is the same. Every time. A University of Baltimore economic study using in-plan modeling estimated the 2016 flood alone reduced Howard County economic activity by up to $42.4 million. 141 businesses sat in the directly impacted corridor. 955 jobs depended on them. A historic downtown, buildings that had stood since before the Civil War, was nearly destroyed by a rainfall event that lasted less than 3 hours. The community rebuilt. Business owners shoveled mud, replaced inventory, reopened their doors. And then, 22 months later, the identical mechanism destroyed it again. Some owners, already stretched thin by the 2016 recovery, simply couldn't come back after 2018. The question hanging over Ellicott City after the second flood was no longer whether it could happen again. It was whether the town could survive a third occurrence of something the physics guarantees will repeat. 4 events now sit in front of you. 1962, a stalled coastal nor'easter delivering surge over 5 tidal cycles across 3 days. Ida, 2021, extreme urban rainfall, overwhelming combined sewer infrastructure in hours. South Carolina, 2015, a cut-off low pumping moisture over the same ground for 4 days straight. Ellicott City, terrain and impervious surfaces converting extreme rainfall into a wall of water in minutes. 4 different locations, 4 different decades. And they share one variable that almost never appears in the headlines or the official damage reports: how long the storm sits still, the duration of the input. And this is where the compound picture assembles. Because on the I-95 corridor, you don't face one of these failure modes in isolation. You face all of them at once. Part 9, the compound picture. And this is where the 2 threads of this investigation finally meet, where the mechanism and the history converge on a single conclusion that most flood planning on the East Coast has never been forced to confront. Everything I've assembled across the last 8 parts has been evidence of individual failure modes operating independently. Coastal surge stacking over multiple tides, that's the 1962 story. Urban flash flooding on impervious ground, that's Ida. Multi-day rainfall from a cutoff low acting as a moisture pump. That's South Carolina. terrain-amplified flash, flooding through converging watersheds. That's Ellicott City. Each one killed people. Each one reshaped communities. Each one overwhelmed the specific piece of infrastructure designed to handle that specific type of flood. But that's the key problem. The infrastructure is designed to handle specific types. The FEMA flood maps treat coastal flooding and riverine flooding as separate risk zones with separate return periods. The slosh model handles storm surge. A different set of rainfall runoff models handles flash flooding. The tidal models handle coastal inundation. Each system is tested against its own historical record. Each performs reasonably well in isolation. But the I-95 corridor between Washington and Boston doesn't face these threats one at a time. A cutoff low parked over the mid-Atlantic bight delivers all of them simultaneously, and the interaction between them isn't additive, it's multiplicative. That distinction is the core of everything that follows. There is a peer-reviewed framework for this. In 2020, Bavacqua and colleagues published a study in Communications, Earth, and Environment that quantified how the simultaneous occurrence of multiple flood drivers, what the literature calls compound flooding, is projected to change as the climate warms. Their central finding, under a high emissions scenario, the probability that rain and coastal flooding hit at the same time increases globally by more than 25% by 2100. But the number that genuinely caught my attention was the regional projection. In latitudes above 40 degrees north, which captures the entire stretch from Washington to Boston, every city I've been discussing, compound flooding events could become more than 2.5 times as frequent as they are today. The study decomposed the drivers. Extreme precipitation accounts for 77% of the projected increase. Elevated tides from meteorological forcing account for another 20%. 77 and 20, rain and tide. Now think about what a cutoff low parked over the mid-Atlantic bight delivers. Rain and tide, continuously for days. The exact two drivers that Bavacqua's analysis identifies as responsible for 97% of the increase in compound flood risk, delivered by the exact mechanism this investigation has been tracking from Part 1. The specific physics of why compound flooding is more destructive than any individual flood source come down to one thing: drainage. Under normal conditions, stormwater runoff flows downhill through the sewer network, through outfall pipes, and into the harbor or the rivers or the tidal canals. Gravity does the work. The system was designed around that gradient. But when persistent onshore wind from a stalled storm piles ocean water against the coast, the way the Ash Wednesday storm did across 3 days in 1962, the way the 2015 South Carolina cutoff low did for Fort Ock, the harbor water level rises. It rises above the elevation of the storm sewer outfall pipes. The NOAA Compound Flooding Technical Report describes the result. Elevated coastal water levels inhibit the efficient gravity drainage of storm sewers and rivers. In plain terms, the bathtub can't empty because the drain is underwater. The rain keeps filling it from above. The ocean keeps blocking it from below. And the storm that's causing both of them doesn't move. And the bathtub is shaped to make it worse. The mid-Atlantic bight, the concave stretch of coastline between Cape Hatteras and Cape Cod, doesn't deflect storm surge. It traps it. Peer-reviewed oceanographic research has identified what functions as a continental shelf seiche in the New York bight, where surge energy gets trapped and amplified by the concave coastal geometry, bouncing back and forth instead of dissipating along a straight coastline. NOAA's storm surge guidance confirms the broader principle. Surge will be higher when a storm affects a concave coastline than a convex one, and the mid-Atlantic has a second amplifier, a wide, gently sloping continental shelf that extends far offshore. NOAA notes that this configuration allows for higher storm surge because the shallow water provides more surface area for wind stress to push the water column. A slow-moving storm, they add, can push water further inland, especially into bays and estuaries. The mid-Atlantic bight is functionally a bowl, concave coastline, shallow shelf, converging bays, and a parked storm fills it from the top while blocking the drains from the bottom. Every element compounds every other element. Sea level rise raises the starting line. Impervious cover accelerates the runoff. The combined sewer system hits capacity faster. Coastal surge blocks the outfall pipes. The rainfall keeps coming because the storm isn't moving, and the concave coastline traps the surge inside the bowl. Remove any single element and the event is still serious. Stack them together, the compound scenario, the interaction the planning documents were never designed to handle as a system, and you exceed every individual threshold, because the thresholds were set independently. And the emergency response implications of that simultaneity are something I haven't seen adequately addressed anywhere in the public planning documents. When a coastal flood hits, the evacuation routes run inland, away from the water. When an urban flash flood hits, first responders move in from surrounding areas. When a river floods, the communities upstream or downstream that aren't flooded provide mutual aid. But a compound event from a stalled cutoff low floods the coast, and the urban core, and the rivers, and the low-lying inland areas, simultaneously across the same geography for the same multi-day duration. The mutual aid model assumes that somewhere nearby is dry and available to help. A compound event challenges that assumption at its root. Hahn and colleagues published a 2024 study in Water Resources Research examining compound flooding, specifically in Norfolk and Virginia Beach, the segment of the I-95 corridor where relative sea level rise is fastest. Their work represents one of the first serious attempts to model the nonlinear interaction between coastal surge and inland rainfall-driven flooding in that region. The fact that a peer-reviewed study attempting this for even a single metro area along the corridor didn't arrive until 2024 tells you something important about the distance between the threat and the research infrastructure tracking it. A previous episode on this channel walked through what the Salinger hotspot data means for the Norfolk-Hampton Roads region specifically, the land subsidence, the aquifer compression, the possible AMOC signal. If you watch that investigation, you'll recognize the sea level numbers from Part 4. What's new in this episode is the compound framing. Sea level rise is not a standalone risk factor. It's the baseline modifier that makes every other threat, due rainfall intensity, storm surge, drainage failure, CSO overflow, measurably worse. It raises the floor, and every other factor builds on top of that elevated floor. Because the data on storm stalling is newer, more contested, and more alarming than almost anything else assembled in this investigation. If the storms are demonstrably slowing down, parking longer over the same ground, delivering their rainfall loads over narrower geographic areas for longer durations, and the coast is rising, and the ground is paved, and the sewers are already at capacity under routine rain, then the compound scenario isn't a historical curiosity drawn from 1962. It's not an artifact of one bad week in one bad decade. It's a converging trend built from multiple independent data streams, each one documented by a different research group using different methods, and each one pointing in the same direction. The evidence for that convergence comes from two independent research teams, tracking the same signal from different angles, and both of them find it. Part 10, the storms are slowing down. In 2018, James Cosson, then at NOAA's National Centers for Environmental Information, one of the country's primary climate data archives, published a paper in Nature that sent a quiet shockwave through the atmospheric science community. The finding was straightforward, but its implications were enormous. Cosson tracked the translational speed of tropical cyclones globally using the best available track data going back to 1949, and found that storms were moving across the Earth's surface more slowly than they used to. Not dramatically, this wasn't a cliff. Not overnight. The change emerged over decades, but measurably, persistently, and in a direction that has devastating implications for everything I've been building across this investigation. Because a slower storm is a storm that parks longer, and duration, as 12 parts of evidence have now demonstrated, is the variable that turns a weather event into a catastrophe. A year later, Cosson teamed with Timothy Hall at NASA's Goddard Institute for Space Studies and published a follow-up in NPJ Climate and Atmospheric Science that narrowed the lens to the place that matters most for this episode, the North American coast. They examined every tropical cyclone in the HERDAT database from 1944 through 2017 that lingered in a coastal region for more than 2 days. 66 storms met that threshold over 74 years. That's not a huge sample. It's part of why the statistical debate is legitimate, but the distribution of those 66 storms across the record is what caught my attention and held it. In the first third of the period, roughly 1944 through 1968, 17 storms stalled near the coast for more than 2 days, 17 in 24 years. In the middle third, the count rose moderately, but in the final third, roughly 1993 through 2017, nearly half of all 66 qualifying storms occurred. Not a third, nearly half. The clustering toward the recent period isn't subtle. It's not a matter of squinting at the data and finding a pattern. It's visible in the raw count, and it runs in the direction you'd expect if the atmospheric circulation were weakening. Kossin was direct about what the climate models predict. He stated that the vast majority of models consistently predict a slowing of the tropical circulation due to human-caused global warming. The proposed mechanism is intuitive once you see it. As the Arctic warms faster than the tropics, a pattern called Arctic amplification that's been documented extensively, the north-south temperature gradient that drives the large-scale atmospheric circulation weakens. Think of that gradient as the throttle on the jet stream's engine. Reduce the temperature difference and you reduce the engine's power. The steering currents that push weather systems along lose velocity, and when steering currents weaken, storms don't barrel through anymore. They drift. They meander. They park. But I have to be honest with you about where the science stands on this because the honest answer is also the important one. Hall and Kossin themselves included a caveat in their 2019 paper that I think every viewer of this investigation needs to hear. We make no attribution to anthropogenic climate forcing for the stalling or rainfall. The trends could be due to low-frequency natural variability. That sentence appears in the peer-reviewed paper. The researchers who discovered the signal explicitly declined to assign it a human cause. They saw the pattern. They documented it rigorously. They quantified it, and they stopped there. That's not evasion. That's scientific discipline of the kind this channel respects, even when it complicates the narrative. And the finding didn't go unchallenged. John Lanzanti at NOAA's Geophysical Fluid Dynamics Laboratory, one of the premier climate modeling centers in the world, raised pointed questions about whether the observed translation speed slowdown over ocean areas could be partly an artifact of changes in observational methods. The argument has weight. Before satellite coverage became comprehensive in the late 1960s and 1970s, slow-moving storms over open water were harder to track and easier to miss in the data. Better satellite coverage in the modern era makes slow-moving storms easier to detect and track precisely, which could artificially inflate the recent count relative to earlier decades. Ilju Moon and colleagues published a separate critique the same year from a different methodological angle. The debate is genuine. The attribution question is unresolved in the literature, and I want to be precise about what that means. It means we know the pattern exists, and we don't yet know, with scientific confidence, whether it's being driven by warming or by a natural oscillation that might reverse. What is not in dispute is the observation itself. Jill Trepanier at Louisiana State University published an independent analysis in 2024 examining 1,274 North Atlantic tropical cyclones between 1900 and 2020. Of those, 191, or roughly 15%, met her criteria for stalling, defined as a track contained within a 200-kilometer radius for 72 hours. 72 hours. 3 full days inside a circle, roughly 125 miles wide. That's a storm sitting on top of the same communities, the same watersheds, the same infrastructure for 3 days straight. The stalling events cluster geographically in Trepanier's data, near Florida and the Carolinas, along the central Gulf Coast, in the Bay of Campeche, in the Western Caribbean. The Florida-Carolinas cluster is directly relevant to this investigation because a storm stalling in that region is a storm sitting near or on the coastline where the mid-Atlantic bight begins. Shift it north by a few hundred miles, which is exactly the counterfactual I posed in Part 1, and it's sitting over the I-95 corridor. The pattern is real. The geographic clustering is real. The debate is about the cause, not the existence of the phenomenon. And here is how I think you should hold this, because precision matters, and I'm not going to pretend the science is more settled than it is. The stalling trend is a fingerprint in the data, clear enough to see, too fresh to definitively source. The mechanism that climate models predict would cause it: weakened steering currents from a reduced pole to equator temperature gradient (ARST) exists and is well understood in the theory. But the observational record is not yet long enough, or the signal yet strong enough, relative to natural variability, to close the attribution loop beyond reasonable scientific challenge. Both of those statements are true simultaneously, and this investigation holds both of them all the way through. That's not hedging. That's accuracy. What matters for the I-95 corridor is not whether the stalling trend is definitively caused by climate change. What matters is that it exists, and that it exists in the geographic region that includes this coastline. If storms are parking longer, for whatever reason, then everything I've documented in the last 9 parts gets worse. And the relationship isn't proportional. It's exponential. Consider what happens when you extend a storm's residence time from 1 day to 3. The compound flooding duration triples, obviously. But the rainfall totals don't just triple, because a saturated watershed doesn't absorb the 3rd day of rain the way it absorbed the 1st. By day 3, the ground is full, the rivers are in flood stage, the sewers have been at capacity for 48 hours, and every drop of rain becomes runoff at 100% efficiency. The tidal cycles continue stacking because the onshore winds haven't stopped. The coast that absorbed the first 2 tides is already eroded, already weakened, less able to resist the 3rd and 4th. Duration doesn't just add to the damage. It multiplies the vulnerability of the system to each successive increment. If the stalling trend continues, and neither the supporters nor the critics of the attribution debate dispute that the observational trend exists, then the compound scenario I've been building becomes more probable with each passing decade. Not because the storms themselves are stronger, because they're slower. And slow is what kills you on a paved, sewered, sea-level compromised coastline. And the physics of what happens during those extra days of residence depends on one more variable, one that isn't debatable at all, because it's thermodynamics. Part 11, 7% per degree. A warmer atmosphere is a thirstier atmosphere. It holds more moisture, pulls it off the ocean surface more aggressively, carries it inland in greater volumes, loads it into storm systems like filling a bigger bucket before tipping it over. And when those storm systems finally release the moisture as rain, a warmer atmosphere delivers more water per event than a cooler one would have under the same dynamics. That relationship isn't a model projection. It isn't a contested hypothesis. It isn't a finding that might get revised next year. It is a thermodynamic law, the Clausius-Clapeyron relation, and it has been understood and experimentally confirmed since the middle of the 19th century, before the Civil War, before the telephone. This is not new science. This is physics that was settled before the first weather forecast was ever issued. The rate is approximately 7% more water vapor capacity for every degree Celsius of warming. Think of it as the atmosphere's carrying capacity expanding. A bigger bucket, and here's why that number matters for this investigation specifically. It connects directly to every rainfall figure I've cited across the last 10 parts. 7% doesn't sound transformative in isolation, but apply it across the roughly 1.2 degrees Celsius of global warming that has already occurred since the pre-industrial baseline, and the atmosphere over the mid-Atlantic in June of 2026 is carrying approximately 8 to 9% more moisture than the atmosphere that fed the Ash Wednesday storm in 1962, more than the atmosphere over South Carolina in October of 2015, more than the atmosphere that dropped 7 inches on Central Park during Ida. Every record-breaking rainfall event in the modern era occurred in an atmosphere that was already wetter than the atmosphere that preceded it. And the next event will occur in an atmosphere wetter still. Now combine that with a storm that doesn't move. This is the piece that makes the Clausius-Clapeyron effect genuinely alarming in the cutoff low context. The extra moisture doesn't just intensify one pass of rain. It intensifies every pass, over days, a cutoff low cycling tropical moisture through its circulation for 96 hours in a warmer atmosphere delivers 7% more rain per cycle than the same low would have in a cooler atmosphere, and there are dozens of cycles over a multi-day event. The totals diverge over time because each cycle operates on the amplified rate. By day 3, by day 4, the cumulative excess over what the same storm would have delivered 50 years ago is not a rounding error. It's the difference between a flood that challenges the infrastructure and a flood that overwhelms it. The Philadelphia Water Department understands this intuitively. Their own climate projections, built into the infrastructure planning for the Green City Clean Waters program, model a 9.5% increase in average annual rainfall by 2050. That projection accounts for the Clausius-Clapeyron effect and other atmospheric changes driven by continued warming. It's baked into the engineering specifications. But here's the critical disconnect. The engineering is designed for average rainfall increases distributed across the calendar year. A few more inches across spring and fall. A slightly wetter June. The design accommodates that. What the design does not accommodate is a cutoff low, delivering the extreme tail of the rainfall distribution, the once-in-a-thousand-year event, concentrated into a 96-hour window, on a surface that is 61% impervious, draining into pipes that were already at capacity before the event began. 7% more moisture in an atmosphere that's already producing a 1,000-year rainfall rate doesn't just push the total a little higher. It pushes it past the threshold, where the infrastructure transitions from stressed to failed. And that threshold, for most of the combined sewer systems along the I-95 corridor, isn't very far above the current design capacity. Central Park's long-term September average, looking at the full historical record, is about 4.31 inches for the entire month. Ida dropped more than 7 in a matter of hours. That excess over the monthly average U, the violence of it, the extreme concentration into a narrow time window, Sieltz, is exactly what breaks engineered systems. And a warmer atmosphere makes that kind of concentration more likely, not less. The extra moisture doesn't distribute itself politely across more drizzly afternoons. The physics is clear on this. The additional water vapor preferentially loads into the most intense convective events, the events that are already the worst. The rich get richer, the extreme tail gets fatter, and the infrastructure sitting below that tail was designed for a thinner one. NOAA's own assessment of sea level rise, and this is a separate but convergent data stream, a third independent signal arriving from a completely different direction, characterizes the current rate of rise as greater than during any preceding century in at least 2,800 years. That number keeps stopping me because of what it implies about how far outside historical experience we already are. The ocean is rising at a pace unprecedented in the observable geological record. The atmosphere is loading more moisture at a pace governed by thermodynamics that's been settled since the 1850s, and the storms may be slowing down at a pace visible in the last 74 years of tropical cyclone data. 3 independent signals, 3 independent data streams, 3 different research communities arriving at the same conclusion from different directions, all 3 making the compound scenario from Part 9 worse in the same way by extending the duration, increasing the volume, and raising the baseline on which the event is built. And every year that passes without a major compound event on the I-95 corridor is not a year of safety earned. It's a year of compound risk accumulating. The sea level at the battery is higher this June than it was last June by roughly 3 millimeters. At Norfolk, nearly 5. The atmosphere over the mid-Atlantic carries fractionally more moisture than it did 12 months ago. The impervious cover hasn't decreased. If anything, it's grown with continued development. The combined sewer pipes haven't expanded. The outfall elevations haven't risen. Every variable moves in the same direction every year, and the interval between now and the next parked storm is a countdown, not a reprieve. The event doesn't have to be unprecedented to be catastrophic. It just has to meet the infrastructure where the infrastructure actually is, not where the planning documents assume it to be. And this is where I need to address something that comes up in the comments of every video on this channel that covers a major flood event. Because when the damage is this extreme, when the failure is this complete, when the numbers look this far outside normal experience, Some people reach for an explanation that involves human intent rather than human negligence. The claims are specific, they're named, they recur after every disaster, and the people making them deserve an actual answer grounded in actual physics, not a dismissal, but an engagement. Part 12, the conspiracy that's wrong and the human fingerprint that's real. The claims show up within hours of every major flood, every devastating hurricane, every weather event that exceeds what people thought was possible. HAARP, the High Frequency Active Auroral Research Program, can create or steer storms. Directed energy weapons cause the flooding. The government is engineering weather events to punish specific regions, displace populations, or advance particular political agendas. The claims are specific and they recur with remarkable consistency. After Hurricane Milton hit Florida in October of 2024, social media was flooded with posts claiming HAARP caused the storm, circulating footage of unusual cloud formations as supposed evidence. The footage turned out to be recycled video of Espiritas clouds from 2021's spurt, a naturally occurring, visually dramatic cloud type that has zero connection to any weapons program or research facility. The video wasn't even from the same year, let alone the same event. I want to take these claims seriously for a moment, not because they're right, they're not, and I'll prove that with specific physics in a minute, but because the impulse behind them is understandable, and dismissing the impulse along with the claim is both unfair and strategically foolish for anyone who wants to communicate honestly about weather and climate. When the water rises to your doorframe for the third time in a decade, and the official explanation is, the atmosphere is complicated, and we're still studying it, that answer feels insufficient. When the forecast model said the storm would move on, and it didn't, when the damage exceeded every official projection by a factor of 2 or 3, when the infrastructure you were told was adequate failed catastrophically while protecting the neighborhoods with newer construction and higher income. The desire to identify a human actor, someone who chose this outcome, someone who could be held accountable and stopped, is a rational emotional response to an experience that feels irrational. The conspiracy is wrong, but the impulse is deeply human, and it persists because the real explanation, systemic, distributed, nobody's fault, and everybody's fault, is harder to hold in your hands. So let me talk about the physics. HAARP is a research facility in Gakona, Alaska, a remote site roughly 200 miles northeast of Anchorage. It is funded by the National Science Foundation. It studies the ionosphere, the electrically charged layer of the atmosphere between roughly 30 and 600 miles above the Earth's surface. This is not the troposphere, where weather happens. The ionosphere is above the stratosphere, above the mesosphere, in a region so far removed from surface weather that the connection between the two is essentially non-existent for the purposes of any energy scale analysis. NOAA's own fact check, published in October 2024 in direct response to the Milton conspiracy claims, describes HAARP as basically a large radio transmitter. Their language, not mine. NOAA states explicitly that the facility is not capable of influencing local weather at Earth's surface, let alone tropical cyclones thousands of miles away. The energy argument seals it. HAARP's maximum transmitter output is measured in single-digit megawatts. A mature hurricane releases heat energy equivalent to a meaningful fraction of total global electricity generation needs. We're talking about a system that processes more energy in a single day than many industrialized nations consume in a year. The gap between HAARP's output and a hurricane's energy budget isn't a matter of degree. It is many orders of magnitude, 12 or more. You cannot steer a hurricane with a radio transmitter for the same reason you cannot redirect a freight train by blowing on it. The energy isn't there. It isn't remotely close to being there. You could operate every HAARP transmitter ever built simultaneously for a century, and the total energy output would not influence a single thunderstorm cell, let alone a tropical cyclone. NOAA goes further in their official statement. No technology exists that can create, destroy, modify, strengthen, or steer hurricanes in any way, shape, or form. All hurricanes, including Helene and Milton, are natural phenomena, and they provide the historical proof that should end the debate, because the United States government already tried. Between 1962 and 1982, NOAA funded a program called Project Storm Fury. The explicit goal was to modify hurricane intensity by seeding clouds inside the eye wall with silver iodide crystals, hoping to disrupt the structure and weaken the storm. They flew aircraft into hurricanes. They deployed cloud seeding equipment. They ran the program for 2 decades with dedicated federal funding and some of the best atmospheric scientists in the world. The result, the research was not successful in modifying hurricanes, and Storm Fury was discontinued. 20 years? Federal resources. Direct attempts? Failure. The conspiracy explanation is wrong. But here is where the investigation takes a turn that makes it unexpectedly more uncomfortable, not less. Because there is a real, documented, peer-reviewed human fingerprint on these floods. It's just not the one the conspiracy describes. And the real fingerprint is in some ways more unsettling because it doesn't have an off switch. Urbanization demonstrably amplifies flood peaks and volumes. 61% impervious cover in New York City means 61% of every raindrop that hits the ground becomes instant runoff. That is not a natural condition. That is a century and a half of paving decisions. Streets, parking lots, rooftops, sidewalks, each one individually rational, collectively devastating for drainage capacity. Sea level rise is human-caused. The NOAA 2022 report is unambiguous about both the trend and the attribution. The rate of rise exceeds anything in at least 28 centuries of geological record, driven primarily by thermal expansion and ice sheet mass loss from human-caused warming. That rising baseline elevates every tide, every surge, every coastal flood event. The Clausius-Clapeyron relationship, 7% per degree, the thermodynamic law from Part 11.2, means a warmer atmosphere holds more water and delivers more intense rain, and storms may be stalling more often near populated coastlines, as Hall and Cosson documented, and the debate continues about. Humans aren't steering storms, but we paved the ground they flood. We raised the ocean they surge through. We warmed the atmosphere they draw moisture from. And we may be weakening the currents that used to push them along. The real human fingerprint is distributed across 100 million individual decisions. Every driveway, every parking lot, every ton of carbon, every year of deferred infrastructure maintenance. It's systemic, compounding, accelerating, and it doesn't require a villain in a bunker pressing buttons. It requires looking honestly at a century of urban planning decisions, a century of infrastructure underinvestment, and a century of emissions that have fundamentally altered the planet's energy balance. That is harder to process emotionally than a conspiracy. A conspiracy offers a clean target, find the villain, stop the villain, fix the problem. The real fingerprint offers no such clarity. It requires accepting that the problem is us, collectively, structurally, over time, and that the fix isn't unmasking anyone. It's rebuilding the systems, redesigning the surfaces, and confronting the emissions, work that is slower, less satisfying, and less viral than a conspiracy video, which is exactly why the conspiracy persists. The truth is more unsettling than the conspiracy. We aren't steering the storms. We are loading the dice and raising the water. And the next time those dice come up with a cutoff low over the mid-Atlantic bight, every loaded factor, the paving, the sea level, the moisture, the stalling, compounds at once. Part 13, the question nobody wants to model. So where does all of this leave us? 12 parts of evidence, 4 historical case studies, each one a narrative proving the same thesis from a different angle. 3 compound connections, each one amplifying the others. A debunked conspiracy and a real human fingerprint that's more disturbing than the conspiracy it replaced. And a central thesis that I've now spent more than 10,000 words building toward, which I can state more sharply now than I could at the beginning because the evidence has earned the precision. The stormwater systems, coastal defenses, and flood models protecting 53 million people along the I-95 corridor were designed for storms that move. The one category of storm that doesn't move, The cutoff low is the one they've never been stress tested against. And every compounding variable, the sea level, the impervious cover, the atmospheric moisture, the stalling trend, has moved in the direction that makes the next test harder. The specific reason the stress test hasn't happened comes down to a structural gap in how the models are built. Flood risk on the East Coast is assessed through multiple independent modeling systems, each one specialized, each one maintained by a different agency or research group, and none of them designed to talk to the others. NOAA's slosh model, sea, lake, and overland surges from hurricanes, handles storm surge. It simulates how ocean water piles against the coast under different wind fields, storm tracks, and forward speeds. Slosh is good at what it does. It has been validated against decades of observed storm surge events, but it doesn't model rainfall. It doesn't care what the sewers are doing. It doesn't know whether the ground is paved or forested. It tells you how high the ocean will push inland under a given storm scenario. And that's it. Separate rainfall runoff models handle inland flash flooding. These calculate how much rain exceeds the ground's capacity to absorb it, and how fast the excess reaches rivers, streams, and the storm sewer network. They account for impervious cover, soil saturation, and watershed geometry. But they don't model storm surge. They don't incorporate tide gauge data. They don't know what the ocean is doing while the rain is falling. Tidal models handle coastal inundation from astronomical tides and long-term sea level rise, the slow, chronic flooding that Norfolk experiences on sunny days. Each system is tested against its own slice of the historical record. Each one performs adequately within its lane. But compound flooding, by definition, is the nonlinear interaction between these sources. It's what happens when surge blocks drainage while rain overwhelms the sewers, while the ground is already saturated while the tide keeps rising, because the storm won't move. And that interaction is not captured by any of the independent modeling systems. FEMA's flood insurance rate maps, the documents that determine who buys flood insurance, where buildings can be constructed, what elevation requirements apply, are built on statistical frequency analyses of individual flood sources. The 100-year coastal surge zone is calculated by analyzing the historical record of surge events in isolation. The 100-year riverine flood zone is calculated separately from a different data set using different methods. The maps assume the sources are independent, that a coastal surge event and a major rainfall event are statistically unrelated, like rolling two separate dice. The chance of both happening simultaneously is treated as the product of their individual probabilities. But a cutoff low produces both from the same source. The onshore winds that generate surge are created by the same system that generates the rain. The events are not independent. They are caused by identical atmospheric dynamics, guaranteed to co-occur when the mechanism activates. The dice are loaded, and they're loaded by the same hand. Hahn and colleagues demonstrated this directly in their 20 out of 24 water resources research study of compound flooding in Norfolk and Virginia Beach. Their work is one of the first peer-reviewed attempts to model the nonlinear interaction between coastal surge and rainfall-driven flooding for a specific metro area on the I-95 corridor. When they coupled the sources, allowed them to interact the way physics says they do during a real event, the flood footprint was different from what either source predicted independently. The whole was greater than the sum of the parts, and the gap between their compound results and what the independent models predict is the gap where the thesis lives. It is a quantified gap, demonstrated in a peer-reviewed journal for a single metro area. Nobody has run it for the corridor as a whole, and nobody, as of this investigation, has published a study that combines all four factors for the I-95 corridor as a single integrated scenario. 1962 magnitude tidal stacking over multiple cycles. Ida magnitude rainfall rates sustained for days instead of hours. 2026 sea level baselines across every tide gauge, from Norfolk to Sandy Hook. 61% impervious cover feeding a 150-year-old combined sewer system that overflows half the time it rains under normal conditions. That specific combination, that specific corridor, that specific compound scenario. It hasn't been run through a coupled model, not because it's implausible. I've spent 12 parts, demonstrating that every component is individually documented and quantified. But because the modeling infrastructure treats each source independently, and nobody has built the integrated tool that would force them to interact the way physics says they will, testing each leg of a chair separately and declaring the chair safe without ever asking what happens when someone sits on all four legs at once. That is the gap in the modeling. That is where the thesis lands. And the implications of that gap are not academic. They're the difference between an emergency management plan that works and one that fails on the day it matters most. Because if the flood models underpredict the compound event by even 30%, if the real surge plus rain plus tidal locking total exceeds the independent source estimate by a third, then the evacuation zones are wrong. The insurance maps are wrong. The infrastructure design thresholds are wrong. And the people living in the zones between the modeled line and the real line have no idea they're exposed. And that brings us to the part of this investigation I think matters most, because the evidence I've assembled across 13 parts doesn't converge on a single clean conclusion. It points to three interpretations. All of them are defensible. All of them are grounded in the data I've shown you. The distance between interpretation 1 and interpretation 3 is the distance between a bad week that the system absorbs and a compound catastrophe that exceeds every plan on the shelf. And the data, right now, does not tell us which one is correct. What the data tells us is what each one costs if it turns out to be wrong. Part 14, Interpretation 1. The system holds I have spent 13 parts building a case. Evidence layered on evidence, mechanism on mechanism, historical proof on historical proof. And the honest thing to do now, the thing this channel exists to do, is present the three defensible interpretations of what all that evidence means and let you hold all three at the same time. Because the data supports more than one reading, and pretending otherwise would be the kind of overselling that this channel has committed to avoiding since day one. The first interpretation is the most reassuring. I need to give it genuine weight, not because I'm trying to be balanced for the sake of appearances, but because this interpretation draws on real data that I would be dishonest to minimize. People who hold this view are not naive, and they are not ignoring the evidence. They are reading the same operational data, the same tide gauge records, the same model output, and arriving at a defensible conclusion that the catastrophic compound scenario, while physically possible, is unlikely to assemble in any given season and may be manageable when it does. Cutoff lows often reintegrate into the jet stream faster than the worst-case model guidance suggests. The same model bias I described in Part 2, the tendency of numerical weather prediction to move these systems along too quickly, cuts both ways in practice. Sometimes the models are wrong in the dangerous direction, underestimating the stall and the storm parks longer than forecast. But sometimes the system actually does pick up speed ahead of schedule. A short-wave impulse catches the cutoff. The jet recaptures it, and the low exits the region before the multi-day compound scenario has time to fully develop. This happens. It happens far more often than the catastrophic stall. The vast majority of cutoff lows that form over the western Atlantic deliver heavy rain for a day, maybe two, and then weaken or move on. The archive of East Coast cutoff lows is full of events that produce localized flooding and then dissolved. The 5-day park over the mid-Atlantic bight gathered the Ash Wednesday scenario is the rare exception, not the baseline expectation. A careful assessment acknowledges that rarity. The 2026 Atlantic hurricane season outlook adds another layer to this interpretation. NOAA's May forecast calls for below normal activity, as you see 55% probability, 8 to 14 named storms, reflecting developing El Nino conditions and increased vertical wind shear across the Atlantic main development region. El Nino seasons tend to produce fewer and weaker tropical cyclones in the Atlantic. That matters for the compound scenario because the tropical moisture pipeline that supercharged the 2015 South Carolina flood, the conveyor belt fed by Hurricane Joaquin's outer circulation, is statistically less likely to be available in an El Nino year. Without a tropical moisture source feeding the cutoff low, the system's rainfall totals are substantially reduced. The assembly line still runs, but the ingredient supply is thinner. The cookies, to use NOAA's own metaphor, are smaller. Infrastructure upgrades are real and should not be dismissed. DC Water's Clean Rivers tunnel system, when complete, will capture 249 million gallons of combined sewer overflow per storm event, representing a 96% reduction in CSO discharges for the District of Columbia. That is a genuine, measurable, engineered improvement over the system that existed a decade ago. Philadelphia's $2.4 billion Green City Clean Waters program has already installed thousands of bioswales, rain gardens, permeable pavement installations, and tree trenches across the city, reducing impervious runoff at the neighborhood scale. New York has invested in expanded pump capacity at critical subway stations and has begun elevating vulnerable entrance points based on updated flood projections developed after Ida. These aren't hypothetical proposals. They're physical infrastructure, steel and concrete and engineered soil, that exists in the ground today and that did not exist when Ida hit in 2021. And the atmospheric pattern itself, right now in early June 2026, actively argues against the compound scenario. The current setup is a ridge, heat risk, not flood risk. A progressive jet stream pattern, one where troughs and ridges move through at normal translational speed, prevents the blocking configuration that traps a cutoff low. No block, no cutoff. No cutoff, no multi-day stall. No stall, no compound scenario? The ingredients exist in the medium range. I showed you that in part 1, but the atmosphere hasn't assembled them and may not. This interpretation says the catastrophic compound event is physically possible, but it requires a specific, relatively rare convergence of ingredients: a strong block, a deep cutoff, a tropical moisture source, a perigin spring tide alignment, all arriving simultaneously over the mid-Atlantic bight. The climatological probability of that full convergence in any given year is low. The infrastructure has been partially upgraded since the last major test. The models, imperfect as they are for stalled systems, still provide multi-day lead time that enables evacuation and preparation. The system holds. That interpretation is fair. It is honest. It is supported by operational data. It is also not where the weight of the peer-reviewed evidence sits. And the second interpretation, the one supported by the largest body of published research, requires holding a more uncomfortable set of numbers. Part 15, Interpretation 2. The trends are real. The intermediate interpretation doesn't dispute anything in Interpretation 1. It doesn't claim the catastrophic compound event is imminent. It doesn't dismiss the infrastructure upgrades or the below-normal hurricane season forecast. What it does is zoom out from any single season and look at the trajectory of every variable that feeds the compound scenario. And every single one of them is moving in the same direction. Sea level rise along the I-95 corridor is not slowing down. It is not plateauing. It is not showing signs of the reversal that Parker's 60-year oscillation hypothesis would predict if we were nearing a peak. Salinger's hotspot acceleration is confirmed in the through 2025 tide gauge data, the most recent data available from NOAA co-ops. The rate of rise at Norfolk is still running at nearly 5 millimeters per year. At Sandy Hook, over 4. At the Battery, just under 3. John Boone's identification of the inflection point around 1987 has held up across every subsequent data vintage. The curve bends upward, and it hasn't bent back. The NOAA 2022 Sea Level Rise Technical Report's central projection, 10 to 14 inches on the East Coast by 2050, authored by William Sweetie, has not been revised downward since publication. If anything, interim research updates from the ice sheet modeling community suggest the Greenland and Antarctic contributions may be arriving at rates closer to the higher-end scenarios than the intermediate ones. The floor is rising, every year, without interruption or sign of reversal. Extreme rainfall intensity is increasing across the mid-Atlantic, consistent with Clausius-Clapeyron thermodynamics. Ida's 7+ inches on Central Park occurred in an atmosphere carrying approximately 8 to 9% more moisture than the atmosphere of the mid-20th century. That isn't a model projection. It's a measurement, derivable from the temperature record and the physics. The Philadelphia Water Department's 9.5% average rainfall increase projection by 2050 captures the central tendency, but systematically understates the behavior at the extreme tail of the distribution eye, and the extreme tail is precisely where cutoff low events operate. Published research on rainfall intensification consistently shows that the most intense events are intensifying faster than the average, because additional water vapor loads preferentially into the strongest convective systems. The average gets a little wetter. The extremes get a lot wetter. The stalling trend, documented by Hall and Cosson, contested in its attribution to human forcing, as I was careful to establish in Part 10, but not contested in its observational reality, shows a clear clustering of coastal stall events toward the recent decades of the record. 17 stalls in the first third, nearly half the total in the last third. Trepanier's independent analysis of 1,274 tropical cyclones confirms the geographic clustering near Florida, the Carolinas, and the Gulf Coast. The regions adjacent to the corridor this investigation is tracking. Whether the cause is anthropogenic or natural variability, the trend runs in the direction of increasing compound flood duration. And duration, as every case study in this investigation has demonstrated, is the variable that transforms a manageable event into a catastrophe. Bivacqua's compound flooding projections from 2020 remain the most comprehensive global assessment of how co-occurring flood drivers change under warming. The central result, under a high emission scenario, the probability of rain and coastal surge co-occurring increases by more than 25% globally by the end of the century, but global averages flatten the regional story. In latitudes above 40 degrees north, the latitudes spanning the entire I-95 corridor from Washington to Boston, compound flooding events could become more than 2.5 times as frequent, not 25% more frequent, 250% of the current rate. Bivacqua decomposed the contributions. Extreme precipitation drives 77% of the projected increase in compound flood likelihood. Elevated tides from meteorological forcing contribute another 20%. Those two drivers, rain and wind-driven tide, are precisely, exactly, specifically what a stalled cutoff low delivers. Simultaneously, for the duration of the stall, the mechanism this investigation has been tracking for 18,000 words is the same mechanism that Bivacqua's model identifies as the dominant driver of 21st century compound flood risk in this latitude band. The infrastructure upgrades, while real and commendable, are racing a target that's moving away from them. DC Water's tunnel system will be transformative for Washington's combined sewers when it's finished, but the completion date has shifted, the way large infrastructure projects do, and every year of delay is a year during which the rainfall intensity grows and the sea level rises. Philadelphia's green infrastructure program is genuinely impressive in scope and ambition, but the Philadelphia Water Department's own climate modeling shows rainfall increases outpacing the capture capacity of the installed green systems over the coming decades. The gap between what the green infrastructure can handle and what the atmosphere is increasingly likely to deliver is growing, not shrinking. New York's 61% impervious cover hasn't decreased. The 398 combined sewer outfalls still discharge on the order of 18 billion gallons per year under routine conditions. The upgrades, expanded pumps, elevated subway entrances, revised flood maps are not closing the gap between infrastructure capacity and compound flood risk. They are slowing the rate at which the gap widens. That's progress, but it is not solution. The WPC's own operational language from the June 4th discussion captures the uncertainty with unusual directness. Models significantly diverge on the timing, placement, and intensity of the heaviest rainfall. That kind of divergence isn't decreasing as the atmosphere warms and energizes. Blocking patterns, the mechanism that traps cutoff lows, may themselves be changing in frequency or persistence as the Arctic warms and the jet stream pattern shifts. The forecast uncertainty around stalled systems is itself a variable, and it's moving in the direction of less confidence, not more. The intermediate interpretation says the system is not currently overwhelmed. A compound event hasn't struck the full I-95 corridor in the modern era, but every margin of safety that existed when the infrastructure was designed has been eroded. The sea level is higher. The ground absorbs less water. The atmosphere carries more moisture. The storms may be parking longer. The margins are being consumed from both directions. The water rising from below, the rain intensifying from above, and the rate at which those margins narrow is documented, ongoing, and in several variables accelerating. The honest question isn't whether a compound event will test the system. It's when, and whether the remaining margins will hold when it arrives. That interpretation is where the published literature most directly points. It is the reading of the evidence that the largest number of named researchers cited in this investigation, Salinger, Boone, Sweet, Bivacqua, Cosson, Hall, Trepanier, would most closely endorse based on their own published findings. It is not comfortable, and it is not the most concerning interpretation available. Part 16, Interpretation 3, Ethiopia. The convergence. I don't present this as a prediction. I present it as a physical possibility grounded entirely in evidence that has already been assembled and verified across the first 15 parts of this investigation. A genuine cutoff low forms over the western Atlantic and drifts toward the mid-Atlantic bight. An omega block or Rex block locks into place upstream, trapping the low east of the coastline. The system stalls. The models of you biased, as they reliably are, toward moving the low along, under-forecast the duration. The onshore wind begins. The tides start stacking. The low reaches into the tropical moisture reservoir, maybe a decaying tropical system in the subtropical Atlantic, maybe just the ambient tropical air mass that sits over the Gulf Stream in summer and fall, running warmer and holding more moisture than any comparable month in the historical record thanks to the Clausius-Clapeyron amplification from Part 11, and begins cycling it through its circulation. The moisture arrives from the east and southeast. The low wraps it around its center and delivers it as rain over the same ground, the same watersheds, the same impervious surfaces, over and over. Day 1 delivers heavy rain 4 to 6 inches across the I-95 corridor. The combined sewers absorb the first hour, maybe 2, then overflow. The manholes bubble. The streets flood in the usual places. Emergency management activates. Sandbags deployed. Pumps running. Day 2 delivers heavier rain on ground that's already saturated and on streets that never fully drained from day 1. The 398 combined sewer outfalls in New York City are running continuously by this point, discharging a mixture of stormwater and raw sewage into waterways that are themselves elevated by the persistent onshore wind. The subway system is flooding at the same vulnerable entrance points that failed during Ida, except this time, the water doesn't recede after 6 hours. It keeps coming. In Philadelphia, the green infrastructure is saturated. The bioswales are full. The permeable pavement has reached its storage capacity. Every additional inch of rain runs off the surface exactly the way it would off conventional asphalt. The tides don't recede between cycles because the wind doesn't stop. The harbor water level at the Battery, at Sandy Hook, at the Verrazano Narrows, sits above the outfall pipe openings. The bathtub can't drain. The rain keeps filling it from the sky, loaded with that 7% additional moisture per degree of warming, delivered preferentially through the strongest convective bands that train over the same ground in succession. The mid-Atlantic Bight's concave coastline traps the surge energy. The wide, gently sloping continental shelf amplifies it. By day 3, the scenario is delivering something that mechanistically resembles 1962's tidal stacking. Multiple high tide cycles building on undrained water, occurring simultaneously with rainfall rates comparable to Ida's peak hour, sustained over a much longer period, on a sea level baseline that's roughly a foot higher than anything in the 1962 record, over 61% impervious urban cover in the largest city and comparable impervious fractions in every other metro along the corridor. The specific numbers from the historical record assemble into a composite that has never been modeled, but is physically consistent with every individual component. Coastal surge approaching or exceeding the 1962 peak at Norfolk and Sandy Hook. Rainfall totals in the range of the 2015 South Carolina event, 15 to 20 inches over 4 days, concentrated over the I-95 corridor's impervious surface instead of South Carolina's partially absorbent soil. Combined sewer overflow at sustained maximum discharge for the duration. Subway systems in New York, flooding not for hours but for days. Basement apartments, the same housing stock that killed 13 people during Ida's 6-hour passage, submerged for the duration of the event. The compound effects multiply in ways that the independent models cannot capture. The surge blocks the drainage. The drainage failure amplifies the urban flooding because water that should be exiting through the sewer system is instead pooling on the streets and flowing into buildings. The urban flooding overwhelms the emergency response because the call volume exceeds dispatching capacity within hours. The emergency response can't reach the affected areas because the roads connecting fire stations and hospitals to flooded neighborhoods are themselves underwater, flooded by the same storm that's flooding the buildings the responders are trying to reach. The mutual aid model, the cornerstone of American emergency management, the assumption that a neighboring jurisdiction unaffected by the event will lend resources, fails fundamentally because the entire corridor is affected simultaneously. There is no dry, unaffected neighbor. Philadelphia can't help New York because Philadelphia is flooded. Baltimore can't help Washington because Baltimore is flooded. The geographic footprint of a stalled cutoff low over the bight spans hundreds of miles, and the compound failure cascades across every municipality within that footprint at the same time. Imagine you're the emergency manager for a coastal county in New Jersey, Cape May, or Atlantic, or Ocean. You've received the forecast. The models are divergent. The NWS Mount Holly office has issued a coastal flood watch, extending through multiple tidal cycles. The WPC has a slight risk for excessive rainfall. Your evacuation plan was built for a hurricane, a storm that hits, peaks, and moves on within 24 hours. The shelters are stocked for a one-night event. The mutual aid agreements with inland counties assume those counties are dry. Now you're facing a scenario that lasts 4 days, floods the coast, and the inland rivers, and the urban cores, and doesn't end with a clearing sky on day 2. What do you do on day 3? The plans don't say, because the plans were built for a storm that moves. I am not saying this will happen this season. I am not saying it will happen this decade. I am saying that every individual component of this scenario is documented in the peer-reviewed literature, quantified by federal agencies, and verified against the operational record. The surge levels come from the 1962 historical data and the NOAA co-ops tide gauge trends. The rainfall rates come from the Ida and South Carolina observations. The impervious cover comes from the 2012 urban forestry study. The CSO volumes come from the New York State DEC. The Clausius-Clapeyron amplification comes from thermodynamics. The stalling trend comes from Hall and Cosson and Trepanier. The compound interaction framework comes from Bivacqua and Hahn. No element of this scenario is speculative. The only thing that's missing is the integrated model that forces them all to interact at once on the same geography at the same time. And the reason that model doesn't exist is not that the scenario is implausible. It's that the modeling infrastructure was built in silos. The data assembled in this investigation doesn't tell us which of the 3 interpretations is correct. The data tells us what each interpretation costs if it turns out to be wrong. Interpretation 1 being wrong means the system faces a compound event it was told was manageable and finds it catastrophic. The cost is measured in lives and infrastructure failure. Interpretation 2 being wrong in the optimistic direction costs relatively little. We overbuilt some tunnels, overprepared some evacuation plans, invested more than we strictly needed to. Interpretation 3 being wrong in the pessimistic direction, meaning the catastrophe exceeds even the worst-case physical scenario assembled here, would require an event outside the evidence bounds of this investigation, which I'm not going to construct. What I will say is that the asymmetry of those costs, the gap between we overprepared and we weren't even close, should inform how seriously the compound scenario is taken in planning, even by people who find interpretation 1 most persuasive. Part 17, what we know, what we don't, and what would settle it. There is a discipline to separating what is settled from what is contested from what is unknown. This channel tries to practice that discipline in every episode, and this investigation has generated enough evidence across 16 parts that the sorting is worth doing explicitly. What is settled? Sea level rise along the northeast coast is real, documented by continuous tide gauge records stretching back more than a century at some stations, and accelerating in a defined hotspot running from Cape Hatteras to Boston. The acceleration was identified by Salinger in 2012, confirmed by Boone's inflection point analysis, and has persisted through every subsequent data vintage. The human contribution to that rise, through thermal expansion of warming ocean water and mass loss from the Greenland and Antarctic ice sheets, is supported by the overwhelming weight of peer-reviewed evidence and by the institutional consensus of NOAA, NASA, and the IPCC. This is not in serious scientific dispute. Combined sewer systems across the I-95 corridor overflow routinely under conditions far less severe than a multi-day stalled storm. NYC's 398 outfalls, Philadelphia's aging system, Washington's pre-tunnel infrastructure, all documented, all quantified, all discharging billions of gallons annually into the same waterways that would be elevated by a compound surge event. Impervious surface cover in New York City exceeds 60%, the highest of any major metro area studied. This is a measured quantity from published research, not an estimate. Cutoff lows, park when blocked. This is definitional. The NWS definition, the operational forecast literature, and the 2024 Pinheiro study all confirm that the mechanism is well understood, even if the forecast of any individual event's duration is uncertain. Numerical weather models systematically underestimate the stall duration. This too is documented in the operational literature. Compound flooding, the nonlinear interaction between coastal surge, rainfall-driven flooding, and drainage failure, is a defined, peer-reviewed mechanism. Bavacqua quantified its projected increase. Hahn demonstrated its nonlinear behavior in a real metro area. NOAA's own compound flooding report describes the tidal locking drainage mechanism. These are findings, not hypotheses. What is contested? Whether the observed increase in storm stalling near the North American coast is driven by human-caused climate change or by natural multi-decadal variability. Hall and Cosson documented the trend rigorously, but explicitly declined to assign an anthropogenic cause. Their caution was scientific, not political. The record length is short relative to the timescales of natural variability, and the signal-to-noise ratio doesn't yet allow confident attribution. Lanzante and Moon raised legitimate, peer-reviewed methodological challenges from different angles. The debate is active and unresolved as of this investigation, and it may remain unresolved for another decade or more of data collection. Whether the acceleration in East Coast sea level rise identified by Salinger represents a secular trend driven by ice sheet dynamics and ocean circulation changes that will continue indefinitely, or whether it includes a component of natural multi-decadal oscillation that may partially reverse over the coming decades. The mainstream consensus strongly favors the secular interpretation, but Parker's contrarian analysis is peer-reviewed, methodologically coherent, and cannot be dismissed without direct engagement with its statistical arguments. I presented it fairly in Part 4 and continue to hold it as a minority but legitimate perspective. Also contested, the rate at which infrastructure upgrades are actually closing the gap between current drainage capacity and projected future compound flood intensity. The engineering investments are real. The question is whether they're fast enough and large enough to match a threat whose intensity is increasing on multiple fronts simultaneously. DC Water says yes, catastrophic for Washington. Philadelphia's modeling suggests the gap is narrowing but not closing. New York's system, at 61% impervious and 18 billion gallons of annual CSO discharge, faces the largest challenge. Nobody has published an integrated assessment of whether the collective upgrades across the full corridor are keeping pace with the collective increase in compound risk. What would settle it? The honest answer, and I recognize this is uncomfortable, is that the next major cutoff low event over the mid-Atlantic bight would function as a natural experiment, not a planned one, not one anyone should hope for. But the event, when it occurs, will generate data that directly resolves the key uncertainties in this investigation. Specifically, the storm's duration in days would test the model bias. If the numerical models forecast a 2-day event and the system parks for 4, the systematic underestimation I described in Part 2 is confirmed for the modern generation of models operating on a modern atmosphere. The rainfall totals, measured against station records at Central Park, Newark, Philadelphia International, BWI, and Norfolk International, would calibrate against the Clausius-Clapeyron expectation are the totals running 7 to 9% above what the same dynamics would have produced in a cooler atmosphere. The tide gauge readings at the Battery, Sandy Hook, Atlantic City, Baltimore, and Sewell's Point, measured against the through 2025 baselines I documented in Part 4, would reveal whether the compound surge plus rainfall total exceeds what the independent source models predict. That margin of exceedance, the difference between the compound reality and the independent source estimate there, is the empirical test of whether the planning documents are adequate or structurally underbuilt. And the real-time performance of the upgraded infrastructure would provide the most important data of all. Will DC Water's tunnel system, at whatever stage of completion it has reached, capture the overflow? Will Philadelphia's green infrastructure absorb enough to make a measurable difference? Will New York's elevated subway entrances and expanded pumps hold against sustained multi-day input? Those answers don't exist in any model. They exist only in the next event. That natural experiment will occur. Cutoff lows form over the western Atlantic with some regularity. Blocking patterns are a recurring feature of the mid-latitude atmosphere in every season. The convergence of a strong block, a deep cutoff, and a moisture source is uncommon in any given year, but inevitable over a span of decades. The question is not whether the next compound event will arrive. It is when, and whether the margins this investigation has documented will still be wide enough to absorb it when it does. The data doesn't resolve the competing interpretations today, but it specifies, with the kind of precision that permits verification, exactly what to watch, which tide gauges, which station numbers, which forecast products, which thresholds, the ability to name the instrument, name the station identifier, name the specific observation that would confirm or refute the thesis A, that is the difference between vigilance and anxiety. Vigilance is watching a name gauge for a name threshold. Anxiety is worrying about everything and watching nothing. This investigation is built for the first. Part 18 will be watching. The Western Atlantic trough from Part 1 is still out there in the medium range guidance. It hasn't cut off. The ridge over the eastern United States is still holding. The heat risk the WPC flagged for the mid-Atlantic coast this weekend is the immediate story, not the flood scenario this investigation explored. But the ingredients don't go away because the pattern didn't assemble this week. The sea level trend at Norfolk's Sewell's Point gauge, station 8638610, will add another fraction of a millimeter before this episode airs. The combined sewer outfalls in New York will overflow the next time it rains hard, which the climatology says will be soon. The atmosphere will carry slightly more moisture tomorrow than it did today, because the ocean is still absorbing heat and the physics doesn't pause. I'll be watching the WPC excessive rainfall outlooks as they update twice daily out of College Park. The CPC probabilistic hazards discussions that flag the medium-range threats before the deterministic models converge. The area forecast discussions from NWS Mount Holly and NWS Upton and NWS Sterling and NWS Wakefield, the 4 offices whose forecast areas tile the I-95 corridor from Norfolk to New York. The tide gauge data from the Battery and Sandy Hook and Atlantic City and Sewell's Point, updated every 6 minutes, publicly available on the KEOOPS website, numbers that any viewer of this video can pull up and check for themselves. The KDIX and KOKX and KLWX and KAKQ radar composites that show you in real time whether rain is training over the same ground in succession, or moving through the way the planning documents assume. These are not abstractions. They are instruments. They have station numbers. They generate data in real time. And they are the early warning system for a compound event that hasn't been modeled, but has now been described with enough specificity across 18 parts that the next occurrence will be measurable against the framework this investigation has built. If you've watched this far, you're part of the community that watches this data alongside me. That matters more than I can easily say, because the institutional systems, the models, the maps, the planning thresholds were built for a different coastline under a different atmosphere. The gap between what those systems assume and what the compound physics delivers is a gap that only gets filled by people who pay attention to the data and hold the institutions accountable to what the data shows. That's what this channel does. We watch. We name the uncertainty. We hold competing interpretations honestly and tell you what each one costs. And we come back when the story moves. The trough is still out there. The tide gauges are still running. We'll be watching.